Hello fellow engineers, welcome again. It has been a gap of few weeks, but I was busy doing many interesting things with radio astronomy instrumentation. So with the starting of new year, I am back with the next episode of the web series, which is based on developing front-end systems for radio astronomy. And if you could recall from our previous videos, what we have finished so far is all the core electromagnetics part of the system. And now we are going to shift our focus to active devices. So once we got our signals in the coaxial cables, the very next stage which comes in any front-end system is an amplifier, and an amplifier with a low noise. So the unit which I have in my hand is one of my low noise amplifiers, which are for L-band radio astronomy. And as you could see, it's a completely packaged solution where you have input which goes to the antenna, an output which could go to your subsequent RF system, and a bias with which you could bias the low noise amplifier and have very nice gain with very less noise added to it. But reaching to this particular stage is not easy, and it requires years of practice plus sound theoretical knowledge to design a low noise amplifier. Very briefly, we will have a look at the theory of low noise amplifiers. Then the next part of this video or continuation of this video would be the actual measurements of this particular low noise amplifier with a vector network analyzer. And the last part of this video, the part 3, would be really a cool experiment where we will try to measure the noise temperature of this particular device, a low noise amplifier, using a liquid nitrogen. So let's start with the first part, where we are going to focus on the theoretical aspects of low noise amplifier. And since our focus is mainly for radio astronomy, let's try to start with what sort of specs we need while developing an amplifier for radio astronomy instrumentation. So I hope you could see on the screen the typical specs which you need is, of course, the gain of the amplifier, the frequency bandwidth, that from which frequency it starts giving that particular gain and where it stops. Then the gain flatness. It means in the given frequency bandwidth, what is the maximum deviation of your gain. Followed by most important criteria, that is the noise temperature of your low noise amplifier. It is usually expressed in kelvins. Some people prefer to characterize a low noise amplifier in a term referred as noise figure, which is also equivalent to a noise temperature by some standard formulas. I prefer to talk in terms of noise temperature because it simplifies the feeling for me. So this particular amplifier, for example, is rated for a noise temperature no more than 35 Kelvin in the frequency band of interest. And what this signifies that with respect to the input of the amplifier, the maximum noise you would add to your signal would be an equivalent to a resistor at the input at a physical temperature of 35 Kelvin. So whatever thermal noise that resistor would generate at the physical temperature of 35 Kelvin would get added to your signal and will get amplified along with the signal at the output. But this is just noise. But apart from the noise, the very most important feature for any amplifier or a low noise amplifier, if you want to use it for amplification of signals, is the unconditional stability of the amplifier. And what is unconditional stability? It means that the amplifier should amplify the signal without any oscillations. If you design an amplifier which is not unconditionally stable but have better noise temperature, in my opinion it is useless because it would oscillate and it would generate a lot of unwanted spurious lines in your spectrum, and it eventually would degrade your signal to noise ratio. Apart from that, like any other microwave device, you would like to have an input matching, say less than -10 dB, and output matching which is -15 dB or -20 dB over the whole frequency band. So let's start while dealing with the design of this particular low noise amplifier. Now, as you could see from this particular package, it has lot of DC input points, and this particular thing is a 3-stage LNA. It means it has 3 amplification stages inside, and for each stage there is a 2 DC bias points per stage. And why 2? I will talk about it briefly. So let's start with the design procedure of low noise amplifiers. So the step 1 in the design is to understand the transistors which we will use for designing a low noise amplifier. The most commonly used transistors for designing low noise amplifier are field effect transistors, and if one wants to be very specific, these are usually high electron mobility field effect transistors. I won't go into detail about what is hemmed transistor or how it operates with the lowest noise, because that would be a completely another video. I will stick with the design procedure of the low noise amplifier. So let's assume that we are the transistor is available in the market and we are simply going to buy it or procure it from some reputed manufacturer, and whatever data given by the manufacturer to us, we will try to study it, understand it, and from that data we will try to implement our low noise amplifier design. So for that, have a look at the screen that I am choosing one particular transistor, which is a hemmed transistor from Broadcom with a number ATF54143. This is also very common transistor for low noise amplifier designs around L-band or mobile bands, for example. And the manufacturer gives the datasheet of the transistor, but along with the datasheet of the transistor, manufacturer usually gives a model of the transistor which you could import in your EDA tool if you have one. I will be stick with my own Python codes for this particular video. You could also download the datasheet, application notes, but most importantly what you need to download is the S parameter files of this particular transistor for given bias point, such that you have the lowest possible noise figure. Usually the manufacturer will state clearly in their datasheet that for what particular bias point you will have the lowest possible noise. For this particular transistor, a drain current of about 40 milliampere is giving reasonably low noise, so I am going to choose that particular dataset for this particular video's design procedure. So let's check that it's somewhere available here. Data for S and noise parameters at drain source voltage of 4 volt and drain current of 40 milliampere. You could download this data and save it on your desktop, and then if you could look inside that data, what you will find is basically the S parameters of the transistor along with the S parameters, so frequency and the S parameters. At the end of the file, let me go down, you will also find the noise parameters of the transistor. So S parameter basically tells you how the transistor would reflect the incoming signal or how the output is matched, how much gain the transistor could give. But the noise parameters, they really tell you what is the noise added by the transistor, and usually it is characterized by F min, which is the minimum noise figure given by the transistor when its impedance is matched in a reflection coefficient referred as gamma opt. This is somewhat tricky to understand in first go, but when we will proceed with the video, I will try to explain further on these lines. So we got our transistor and we got the data set of the transistor. So the next thing to do is to look at the IV curves of the transistor and also at what particular gate bias you would have, say, 40 milliampere of drain current. So you could see on the screen now that the transistor package is shown. I have taken this data from the data sheet of the transistor, and they have also shown the IV curves. That means for particular drain source voltage and for particular gate source voltage, what is the current drawn by the transistor. And also from the datasheet, the manufacturer have stated that about 20-40 milliampere of drain current, you will have lowest possible noise. So step 1 is to understand your device, finding out the optimum bias point for your transistor for the lowest noise. So that step is done. So next step is to look at the S parameters, what you have received from your manufacturer, or if you are using an EDA tool, you could simply simulate your transistor model for the S parameters for particular bias. In this case, I will simply read the S2P file or the data which you have received from the manufacturer, which I have shown before, and I will simply plot those. So what you could see on the screen now is basically S21 of the transistor, that is the gain given by the transistor, and you could see it is about 25 dB or 20 dB within the frequency range of interest. The S22, which is the green line, the transistor is kind of moderately matched, S22 below minus 10 dB all the way from 800 megahertz and above. S12, which is the reverse isolation, that if you could apply the signal on the output side, how much it would come at the input side. And just for the single transistor, it is of the order of minus 25 dB. And magenta line, which is S11, states what is the input reflection for the transistor when it is biased at, say, VDS of 4 volt and drain current of 40 milliampere. If you change the bias of the transistor, definitely these S parameters are going to change. But since we will stick with the particular bias point which we have chosen earlier, we will use these S parameters for the rest of the design. But these S parameters are simply the magnitudes, and that is not enough for low noise amplifier design. What you need to look at the complex nature of S parameters, because you have to design input matching network, output matching network such that you will have the required gain and required noise. So the next step is to look at these S parameters in a complex plane. That is, we have to look at these S parameters in terms of reflection coefficients on a Smith chart. So I hope some of you are familiar with Smith chart. Those who don't, you could refer to any classic microwave textbook. So what you have on the screen now is a Smith chart which I have plotted. Exactly at the center of the Smith chart, the red dot indicates you have zero reflection, and if our system reference impedance is 50 ohm, it means the impedance is also 50 ohm exactly at the center, and the reflection is zero. While on the upper side of the Smith chart, most of the all the impedances are inductive in nature with some real positive real part, while below, the part below horizontal line is basically all the impedances in capacitive nature. This is a really nice tool, and I must say that the old generation of microwave engineers, they use Smith chart a lot, and even without use of EDA tools, they were able to design really good microwave circuits. But nowadays we have computers which are very much advanced. We have our advanced programming, advanced tools for circuit design. So we can use that and say skip all the lengthy calculations which one has to do by hand. So next step is to plot those S parameters on this Smith chart and how they look like. So as you could see on the screen now, again the magenta line is the S11, the reflection coefficient of at the input of the transistor. The green line, which is S22, while the blue line is gamma opt. And what this says that if you could match the source to this particular reflection coefficient, the blue shown by the blue curve, you will have the lowest noise from the transistor. And there starts the trade-off in the design. Have a look. The data from the manufacturer starts at 800 megahertz and it ends at around 10,000 megahertz, which is 10 gigahertz. So the gamma opt starts inductive and slowly it turns anti-clockwise, and for higher frequencies it becomes capacitive. While if you look at S11, at the low frequencies it starts in capacitive nature and then it rotates clockwise fashion, and for higher frequencies it becomes inductive. So as you could see, the S11 rotates in clockwise fashion in Smith chart, while the gamma opt, which gives the lowest noise for the transistor, rotates in counterclockwise fashion. And that itself becomes very tricky while designing the input matching network for the transistor. So next thing to look at is very generic case of a two-port amplifier. So what you have in the middle is the transistor, whose data which you have received from the manufacturer, S11, S12 and so on, all S parameters. Then at the source you have a source impedance, which is typically 50 ohm for example, or it's the impedance with which your antenna is matched. At the output you have a load impedance, which is also typically 50 ohm. And then you have to design some sort of input matching network, some sort of output matching network, such that first your entire amplifier is unconditionably stable. Second, you got the noise which you wanted. That means you were able to match the transistor such that you got the noise figure which you desired. And thirdly, you got reasonable power matching at the input port and moderately good power matching at the output port. I said reasonably good input matching because usually LNA sits very close to the antenna, and usually it is directly connected to antenna in most of the radio astronomy applications. So one could live with somewhat degraded S11, but what is most important is the lowest noise at the very first stage in your system. So what sort of input matching network or output matching network depends really on your transistor, your frequency range, and how you would like to implement it, like in terms of lumped components or in terms of distributed components such as transmission lines, microstrip lines, stubs, etc. But still, one could try to summarize some common matching networks. And before going there, we have to also think that in order to achieve the maximum power transfer, the gamma source, that is the reflection coefficient on the source side, should be a complex conjugate of the input reflection coefficient of the transistor. The load reflection coefficient should also be a complex conjugate of the output reflection coefficient of the transistor. For the best noise, you should have source reflection coefficient very close to the optimum reflection coefficient at which you have lowest noise. And finally, the stability. It has the stability factor K has to be greater than 1. These are a lot of technical parameters, and there is a lot of theory behind these parameters and why the K has to be greater than 1 and so on. So if you want to look into the theoretical aspects of these things, I would highly recommend a book, and the link for the book is already in the description. You could check that link and check that book, which is really good for low noise amplifier design. And then with this condition set, you could try to think of some sort of matching network for the transistor. But before going there, we have to make sure that our transistor is unconditionably stable. It means that the feedback factor is such that there is no oscillation in our amplifier, and usually this is achieved by adding some sort of stability resistor at the drain of your transistor. People achieve stability by either putting some sort of negative feedback using a shunt resistor. Sometimes people try to put a feedback directly between drain and gate. Sometimes people try to put a feedback between source and ground. So there are different techniques to achieve a negative feedback. In this particular design and in this particular set of problem, I have tried to achieve the unconditional stability for the transistor by adding a shunt resistor at the output of the drain and before the output matching network. With stability problem solved, next step in the design is to then think of input and output matching network. But before going there, if you could recall from earlier Smith chart data, that the manufacturer has given us the transistor data between 800 megahertz and 10 gigahertz. While we want to do a design say between 500-600 megahertz to 1.5 gigahertz, 1.6 gigahertz. In this case, you have an option to extrapolate this data and then use that extrapolated data for your design. So what you could see on the Smith chart now, the blue line is actually the data given by the manufacturer. Rather, the stars are basically, the marker stars are basically the data points given by the manufacturer. And then I have extrapolated this data all the way down to 300 megahertz using some sort of cubic spline type of extrapolation methods. And as you could see, there is a very nice fit between into the given data and the extrapolated data of the transistor. And now I will use the data along the red curve for my design. And the very first thing in the design to do after the stability issue is solved is to look for the input matching network such that the source reflection coefficient is very close to your gamma opt. So then I could think of many different possible matching networks. Usually it has to be a combination of L and C. Avoid a resistor because a resistor is going to add noise before your transistor, and this is definitely you don't want to do to have the lowest noise. So some sort of L and C combination is a possible solution. Of course, for a distributed case, you could implement an inductor with a narrow transmission line, a capacitor with an open stub, and so on. So I have implemented my own matching network, and then what I have done is simulated the source reflection coefficient. That is how 50 ohm source got transformed after introducing some sort of L and C combinations at the input of the transistor. So now you could see it's exactly the same Smith chart as before. You have blue, which is the data from the manufacturer, red is the extrapolated data points, while the magenta line is the gamma opt in the frequency range of interest, that is between 800 megahertz and 1600 megahertz, while green line, which is gamma source, that is the reflection coefficient of the source when 50 ohm source is combined with the input matching network. And as you could see, they are not exactly on top of each other but fairly close, such that for practical purposes we could use that, because when you do a practical design you are limited with the choice of inductor values. You could have very much choices in terms of capacitor values, so you have to think all those practical aspects as well. So you got gamma source, which is very close to the gamma opt. So I hope that with this we will have reasonably well matched transistor for noise. And next thing is to use this gamma opt and gamma source to figure out what sort of noise figure or noise temperature is achieved in our design. So as you could see, the red curve here is the minimum noise temperature if you could match the transistor at the gamma opt for all frequencies of interest. but we have a practical input matching network. So our gamma source is not exactly equal to gamma opt. So what you could see now with the blue curve is the noise temperature of the transistor with input matching network. And there is a discrepancy between the red and blue curve because gamma opt and gamma S, they deviate. They are close to each other but not exactly equal. So in the desired frequency range, say 800 megahertz to 1.6 gigahertz or so, I have a really good noise match for my LNA. But for other frequencies, it's not that good. But still, if you could look at this scale of the noise temperature, say from 600 megahertz all the way up to 1.6 gigahertz, I have a noise temperature of the first stage plus input matching network fairly below 35 Kelvin, which is a very good number for a low noise amplifier design. And then once you are done with input matching network, you are done with the stability. Next is to add your output matching network and then find out the total S parameters of your amplifier. Once you have that, you could simulate your entire amplifier and check its S11, S22, stability and so on. So again, I have done that and I have added another stage to my amplifier, which is a second stage. Of course, I have also implemented an interstage matching network between stage 1 and 2 and then an output matching network at stage 2. So what you could see is a resultant S parameters in this image. So you could see the S11 is fairly well matched. It is below minus 10 dB all the way from 550 megahertz to 1.92 gigahertz. S22 is less than minus 15 dB all the way from 0.55 gigahertz to 1.8, 1.85 gigahertz. The isolation is less than minus 15 dB, less than minus 50 dB in most of the band, which is also good. If you add a third stage, it would also go down, and a practical isolation of 60-70 dB would be really great. While S21 varies from 40-42 dB at the lower frequencies to 36-35 dB at the higher frequencies. So now you could see there is a gain slope, and the difference between S21 at low frequencies and S21 at high frequencies is fairly large, is about 6-7 dB, and definitely we haven't achieved a gain flatness. So when one adds a third stage, typically a designer would try to design an interstage matching network such that it has a nature of high pass. It means it would attenuate your signal at low frequencies, but it would add gain to your signal at high frequencies. So if you could superimpose these two together, you will achieve the desired gain flatness in your overall amplifier unit. And doing some such tricks at the last stage or the third stage of the transistor of your amplifier design is reasonably okay to do, because even if you attenuate a signal, even if you add a little bit of noise, you have already amplified your signal before with a low noise. So the effect on the noise temperature of your entire amplifier would be really less, and you would achieve the desired gain flatness. And then the question is how I have achieved to all these figures without using an EDA tool. Of course, one could use an EDA tool and design the entire amplifier with it. But if you could understand all the theory behind these circuits, and if you could implement your own codes in Python or something similar, you could achieve all these results through your own calculations and through your own codes. So now I will very briefly walk you through my Python code with which I have done all these calculations. And with that, I'm going to stop with the design procedure of this particular amplifier, and I will give some practical tips on the final design. So I will now very briefly show you the Python script which I have wrote for doing my own amplifier design. So basically with the Python scripts using NumPy, SciPy libraries and Matplotlib libraries, I could do all these things which I have shown to you before. So typically what I have in my script, that I import the file which I have downloaded from the manufacturer. Then I try to read that file and try to extract the S parameters and noise parameters. Subsequently, I use some sort of cubic splines fitting to get those S parameters and noise parameters for broad frequency range of interest. Then I use my input matching network and output matching network with L and Cs which I have designed, and for each of my component in my input or output matching network, I try to write its S parameters for the given frequency. And then I convert all those S parameters into transmission parameters, because you could multiply the transmission parameters all together for a cascaded network and get an equivalent transmission parameters. So I do that. I find the total or equivalent transmission parameters of my entire amplifier using all sort of lump components as well as the transistor S parameters. And then I revert back those transmission parameters to S parameters, and I get the S parameters of my entire amplifier module. From those S parameters, I could definitely calculate the stability factor of my transistor, the stability factor of my amplifier, and then plot all these wonderful graphs which you have already seen. So this is very briefly, I have walked you through the Python code. You could write your own codes for doing such sort of analysis. And before I stop, one last thing to check is the stability of my amplifier, because that is the most important factor. Even if I have achieved moderately low noise performance over wide bandwidth. And as you could see from the simulated S parameters of my complete amplifier module, the K of the transistor, or the stability factor of the transistor, just the bare transistor, was way less than 1 over the entire frequency range. But once I add a stability resistor, I add my input matching network and so on, the K or the stability factor of the amplifier stays well above 1 over entire frequency range. This is really important for a good amplifier. So with that, I am going to stop this particular video. I hope you got a rough idea what goes into the design of a low noise amplifier. It's a fairly complex procedure, and different microwave engineers might have different insights into this procedure. I'm going to add another link from Keysight, which is an application note of designing a low noise amplifier using this transistor. The link is in the description. Have a look at it. And then finally, from these lump components and the transistors and S parameters, you have to build a real physical unit of your low noise amplifier. And there many other practical problems comes into the picture. For example, your inductor is never an ideal inductor. It has a finite Q. Your capacitors has finite Q. So you have to model all those L and C's properly, and either you import S parameters of those lumped components into a Python script and do a design. And then you have to also add the DC, the power to your amplifier. And to do that, you have to physically connect the DC power to the drain and to the gate of your transistor. And one common way to do that is shown in the figure, that you would use some sort of choke both at the gate and the drain, such that for the RF, the choke acts as an open circuit, so RF path doesn't see your DC power source, while the choke acts as a short circuit for DC and it supplies the required bias to your gate and drain. Again, you have to add the DC block capacitor at the input and output, such that no external DC could come into your transistor and destroy your device. And also, the stability transistor which I talked about should also have a capacitor in series, otherwise whatever bias you apply at the drain, also that drain current gets splitted between your stability resistor and the drain source current. So these are some practical tips. And finally, you have to built a PCB and enclosed it into a nice fully enclosed metallic chassis, because you don't want any external interference enter into your amplifier. Everything which comes from your coaxial cable should get amplified at the output and no interference should come in. And then while applying DC, of course, using a DC feed through is definitely recommended. So with that, you would complete your low noise amplifier design. So as you could see, it's not so straightforward procedure. It requires a lot of theoretical understanding as well as lot of practical experience. And of course, I have also failed several times before maturing this particular low noise amplifier for radio astronomy. And with that, I'm going to conclude this video, and the next video is to bias this amplifier and start examining its S parameters. Till then, see you.